The next two talks in the session are both from the University of Leeds, so two entrants from the University of Leeds. And the first one will be given by Ritu Munshi. So I don't know if Ritu, you'd like to come forward and maybe share your screen if that's the preference.
Hello. 1 second. Can you please guide me if you're able to see the screen, because I'm in browser?
Yeah, we can see it. It's not in presenter. There we go. That looks right.
Yeah, okay, sure. Hello, everyone. My name is Ritu Munshi, and I'm presenting E012 submission of Cadenza 2023 from University of Leeds. Thank you all for inviting me and selecting our project. And let's start. So we will be going towards the introduction, methodology we use, the system information, and the results we got from that. So why Cadenza challenge? I know it's been discussed a lot before before this, but it's for addressing the specific needs for people with hearing impairment, and the traditional audio is not that much helping in that, or it needs a lot of work together. The reason we went towards Cadenza Challenge 2023 was to bring experiences who are people for accessible, and every person should be able to have a good improved sound quality on each individual level, not a very generic level. So as we all know, there were 4 steps. First was demixing, amplification, remixing, and the calculation of Hagic score. So let's start with demixing. The model in the model configuration, we took the hybrid demix structure. So why with demix? We were like Cadenza challenge provide us with 2 models, the open unmix and demix model. But in demix model, we found a lot of things that is better, like it is able to take the time and frequency, both amplitude together, and they have multiple levels of encoder and decoder, which results in precise separation of audio components, as well as it is very careful in handling the sounds when they overlap each other, which is a very important point, especially when you are working with music. One of the major disadvantages, I will say, comparing with open unmix, was the memory issue. It takes a lot of memory, but thanks to our school, we were given by HPCs, and we worked on that to work on this project. So after choosing our model, what we did was train the same model on MuseDB 18 HQ dataset, and then decompose the stereo order into 8 different steps and resample it to 24,000 steps. After that, we went towards the remixing stage. But after resampling, we made sure that signal are saved in 18-bit audio signals, and compress in audio files using lossless processor, so that it is in the same format and have a uniformity in the data. Our main focus was that we did as a project was towards the remixing. The original remixing were based on solely upon the separation model of like getting the 8 separated stat and summing into 2 numpy array, and it does not take the audiogram of each listener into account. Therefore, it is not tailored, and that's what we wanted to do. We want to have a tailored and improved remixing utilizing audiograms. So first we did was uploading the metadata, which contains audiogram of each user, and compromise the and then categorize the degree of hearing loss is happening in each user. And then after analyzing the programs, we shall go towards input stems and check what is the hearing level. So according to WHO, if the hearing is level in below 20 is non-severe, but if it is above 30, 40 to 50 to 64, it is mediocre severe, and after 65, it is severe. So we want to make sure that we put the multi-band compression and all those sidechain compression only on the people who have severe hair loss and not for the people who haven't. So if there's not, we will just generate the remix signal. But if you have a hearing loss, and depending on the amount, we will go towards the filters and check the filter accordingly. So how the hearing loss confirmation was happening. So what we did was, as I told you, like in the metadata, we were applied, or like we were given with filters, and we chose those filters to work on it and judge the volume, like how much the volume should be changed. So after judging the volume, we had this function of like selecting bands, like which type of band should be there. If the severity is less, it will be at like approx 1 decibel will be added, but the severity is more than 1.5 decibel of is level 1.5 level is added, and then it will into the multiband and side band compression. So why we need those? Like the sidechain compression is helps in ensuring the vocals are very good, and like what multiband compression does is if you go towards low band or right band compression, what happens is if the frequency is above this and the frequency is below this, it will just cut it short, and sometimes it will lead to a very weird audio. So we went towards a multiband compression in which is target to adjust volume to enhance the clarity and the balanced audio approach rather than just the low band and high band approach. And which compression to be applied? We put the sidechain compression for that. In sidechain compression, they try to find the audio in which there is the peak. Like it is necessary to define in multiband compression which bands to select and in which music where is the peak is happening or the climax of vocal is happening, because generally you don't like whichever type of music is, the lot of focus is given on vocals. So wherever the climax of the vocal, we will try to put sidechain compression there. So from that the multiband compression will start. So as you can see in the um, image as well, we can track the vocal and determine which type of compression should be applied for, because there are multiple levels that is defined. Like if the person in the volume, if the person has a normal frequency of hearing in the vocals but have bad frequency of hearing in drums, we can apply the multi-band compression at that level, and similarly the opposite. And after applying those compression, we will get a remixed output. So after the remix output is done, we will do the volume adjustment and ensure the like the balanced audio, like adding the values that are provided in that sense. Well, like 1 dB if there is like in every frequency band we have moderate hearing loss, it will be increased by 1 dB, and if we don't have severe, if we have severe, it will be increased by 1.5. And and this is done by analyzing the audiograms. And similarly, if the individual does not have that much severe and it is less, we can also decrease it by 0.5 dB, and it will result into balanced audio signals. So after that, we got into the Haki score. We saw that our scores are varying across the different songs, and in some it was lower, the some it was higher, but overall it got like the users preferred our audio quality better, and as the marks was declared. And if you go on specific scenes, that it says in some remixed version our volume is below the average. I think it might be due to the reason that while doing the remix on very specific the bass and the drums, it may be the reason of these different scores, because we try to enhance the audio for every user, and it is since so specific towards the user, that might be the reason of this varying score. So in conclusion, I will like to see that if we need a little more work towards the personalized remixing, and if there are further more steps involved regarding further steps and checks regarding from like validated listener, you like the feedbacks we would have given better, like this is the song or the audio is not that much clear. And if we go towards this cycling process, our model can be improved and there can be multiple checks involved before the making remix. We can also enhance demix also, like splitter has been the new one that is very popular right now, and the speed and performance are very good. We can try to do that demix challenge, like improve the demix as well. And yeah, there more the feedback, the more better the work will be. And at last, I would like to acknowledge my professor Julian Brooks and my whole team, because they helped me a lot in this project, and without their help it won't be possible. Thank you so much.
Brilliant. Thank you so much, Ritu, for this summary of this approach that you and the team have taken. We have a bit of time here for some questions. If there's any immediate questions from the workshop, I'd love to open that. Aravindan has the hand up. Would you like to come in, Aravindan?
Hello there. Thank you for the presentation. I would like to know, could you sort of elaborate on the multi-band compression that you're talking about?
Like in why did we use that?
How it was achieved, like the processing behind it.
So like we created a separate file for like multi-band compressor, and this package was imported from enhance.py. And what we did was we import like we initiated to perform, like we initiate the first the sideband, like we implemented two helper functions, like choose the compressor what we want, and to support the system, in which they had two string of identifiers like left vocals, right vocals, and choose which side chain to use. And after that we had the whole bands that we were provided in the, if you chain, like which range is there for the, let me check the, like the word says, like the range for the sidechain compression were there, whatever the hearing losses, there was a whole range, and we were deciding in which range was there, and then we were applying the multi-chain multi-chain compression towards it. Like the frequency bands were given, and after that we select the frequency band, we select the threshold, and after that we go towards that.
How did you choose the frequency bands?
The frequency bands, we analyze the song, and in song there, like there is high vocal, that is it. When the high vocal is it, then they come in certain frequencies. Whenever that peak is reached in the vocal, so that will the climax of that vocal will decide that okay, this is among this frequency band, and that's how we work towards it.
Yeah, that's fascinating. Thank you very much.
Any additional questions from the group before we move on? I maybe just had a very quick question, Ritu, regarding the figure, the graph, the scatter plot of the kind of Hacky scores and comparing the model versus the baseline across the listeners. Well, my assumption was that the individual points were the individual listener audiograms. Do you have a sense, maybe I missed this, but do you have a sense as to where the model is at a disadvantage to the baseline, or where it performs better in relation to audiogram characteristics?
I was trying to determine that. It was like, let me. I think in which like I was not able to determine the whole scores because it came very last minute and I was working. But what I was able to determine in vocals, we are able to like very easily reach. We are like, because the frequency is very easy to determine. So for that multi-band impression is happening very good. But when, as I was telling, one of the reason in some score we are low is we are trying to be very specific towards each individuals. So what we are trying to do also, score the bands for vocals, for music. Like if I'm able to understand the frequency of vocals, I'm not changing it. And if I'm having problem understanding the drums or guitar, I'm just tweaking that bit. So when you are getting that much specific, I think it is failing in some cases.
That makes a lot of sense. Thank you, Ritu.
Thank you.
I think we'll move on to the next talk, and just everyone, please do thank Ritu again for
Sure,
a
thank
wonderful
you.
talk. Thank you.